about he's going to speak about wave equation, no?
Yes,
the
indeed.
topic of your talk.
Yes.
So.
Okay, so thanks to the organizers for giving me the opportunity to talk here and also for organizing this meeting, which is really fun. So I'm going to talk to you about a topic which I started working on already a few years ago in Australia. And it's joint work with a couple of people. It's based on a couple of papers. One of them is together with Andrew Hassel and Pierre Portal from ANU. And there's a separate paper with Andrew, which I'll talk about maybe at the very end. And then there's work with Zijie Fan, Naijia Liu, and Liang Song from Sun Yat-sen University in China, which is also a separate paper. And I decided, so technically I'm supposed to list funding for this whenever I give a talk. So I decided to start doing this. In case there's anyone judging, who's a referee for my grant, you'll know that I actually list my funding. And basically the talk is going to be divided into 2 bits. I'm going to give you a very long introduction. And the reason for that is that the topic is quite technical, especially when you get to the actual proofs. And I'd rather you understand the ideas and the topic than all the details. And then the very last part is the results. So my topic, my talk concerns wave equations. And the best example of a wave equation is just the flat Laplacian on Rn, which gives you the classical wave equation, which looks like this, the abstract Cauchy problem for it. And the topic of my talk today is a simple question. If you have a p between 1 and infinity, you would like to know when the solution is in LP. Note, I haven't specified t here, but I mean that I should have this property for an arbitrary t, which in turn means that I'm considering fixed time LP estimates. I'm not considering Strickhart's or local smoothing type estimates, even though the things which I'm going to talk about actually relate to local smoothing estimates as well, but that's ongoing work. But today I'm interested in the fixed time theory. Now, if you want to answer this question, the first thing to do is to note that you can actually write down what the solution is in this specific case, and it's given in this way. And if you know that, then you also immediately know the answer for P is 2, namely, as soon as F is the initial data is in L2, and as soon as the derivative of the solution at 0 is in W minus 1, 2, then you know that this part, the cosine is bounded on L2, so this part stays in L2, and G gets, heuristically at least, gets mapped back into L2, and then the sine is bounded on L2. So this is easy. Now, unfortunately, it stops being easy as soon as you move to higher dimensions than 1, and as soon as you're not in a trivial case where t equals 0, and p is, and as soon as p is not equal to 2, because then these operators are not bounded on LP. And the reason for that basically is that they're oscillatory operators. The cosine can be decomposed in this way, and similarly for the sine. And this oscillatory integral operator does not map LP to itself, but it's not completely hopeless because it does map a certain Sobolev space over LP into itself. And this Sobolev index is important throughout this talk. For reasons of convenience, notational convenience, I'll write it as 2sp, where sp is this number. You don't have to remember it, but yeah, it is an important number. I'll mention it again in a few slides. And this mapping property is sharp. This index can't be improved, but it does tell you basically the answer to my question from the previous slide, which is what kind of regularity do you need of your initial data to know that the solution is in LP? And basically the initial data F needs to be in this Sobolev space, and G can be in a Sobolev space with -1 differential index. Okay, that's the flat Laplacian. Of course, you're not only going to be interested in the classical wave equation. You'd like to consider wave equations on manifolds and other types of equations. This leads to the theory of Fourier integral operators, which for simplicity, for today's talk, I'll say that they look like this. You can describe them as oscillatory integrals in this way, which consist of, you first take the Fourier transform of a function f, then you multiply it by a function, which depends on both x and eta. And then you multiply it, you have an oscillatory term, which involves a phase function. And then you go, yeah, and that's the expression. And typically, I'm not going to go into details. A is a nice smooth function, which is a pseudo-differential symbol. So it satisfies nice properties. We're not going to get into that. Phi is also smooth, except at where eta is 0. And very importantly, it's homogeneous in the eta variable. And in fact, the fact that it's homogeneous in the eta variable means that it can't be smooth at 0 unless it's linear. And it satisfies some other properties. And in fact, these are not what FIOs really are, but because those are more general operators. But for simplicity, we'll talk about them in this way. Now, instead of defining them in detail, I'm going to give you a few examples. The simplest example is the case where the phase function is the standard phase function, and A does not depend on X. In that case, you just get the operator which takes the Fourier transform of f, multiplies it by a function, and then you take the inverse Fourier transform. And I'll denote such an operator as AD. This will appear again later, and these are Fourier multipliers. If you let A depend on X and eta, but you keep the phase function simple, then you get pseudo-differential operators, which won't play much of a role in this talk. And most importantly, if you change the phase function in this way, and the symbol actually becomes really simple, it's 2 pi to the minus n, then you get back the classical wave equation, or actually the half-wave propagator, classical half-wave propagator. So you can describe, and that's the point of this last example, you can describe wave equations, their solutions, in terms of FIOs. And that means that if you want to answer my question about LP regularity of wave equations, then you need to say something about LP regularity of FIOs. And more precisely, you can do this for any smooth wave equation. You can, as long as you could say slightly more, and you have to make the definition of an FIO slightly more general, then you can write them in terms of FIOs. Now, luckily, there was a fundamental, extremely powerful result by Siegersog and Stein in 1991, who showed that the same mapping properties that you had for the classical wave equation also hold for general FIOs. I should say, yeah, FIOs of order 0 associated with a canonical, local canonical graph, whatnot, but we're not going to say that. And again, I remind you that this index is the same. I also note that this -1 is what's really powerful about this result. It's relatively easy to get the result without the -1. That doesn't involve, that you can do using only harmonic analysis, the theory of spectral multipliers. If you want to get the -1, then you need microlocal analysis. And you can even describe why you actually need microlocal analysis for this in a heuristic way. Now, for the purposes of this talk, it's useful to note that you can also write it in this more symmetric way, where it maps WSP into W minus SP. So that's FIOs and mapping properties. Now, let's go back to the theory of parabolic or elliptic equations, which is much nicer, because those equations do map LP into, the solution operators do typically map LP into itself for P strictly between 1 and infinity. And in this sense, hyperbolic equations are quite different. But even for for singular integral operators or pseudo-differential operators, the solution operators to elliptic and parabolic equations, they don't map L1 into itself, and they don't map L infinity into itself. So there you also see some problems. But there is a solution to this problem, in a way, you could say, because those operators map the local Hardy space, or the global Hardy space when you're considering convolution operators, but the local Hardy space if you consider pseudo-differential operators. They map those into itself, and that space is contained in L1. And even more, it's the biggest subspace of L1 that has this property. So it's a really natural space, which is invariant. And if you know the fact that these operators leave this space invariant, then you can interpolate with L2 bounds to get back everything you need to know about LP. So this is a really natural concept. And in fact, Sigersog and Stein proved their result by showing that if you have a Sobolev space over this local Hardy space, then you, oh wow, I'm already almost out of time. No, I think there was more time because we had a break. They proved it in this way. So that brings us to the following question. If there's a natural invariant space for pseudo-differential operators, for singular integral operators, shouldn't there be some sort of natural invariant space for Fourier integral operators? And you can abstractly even say that this has to be the case because under suitable assumptions, FIOs form an algebra. And then basic algebra means that there has to be an invariant space. Now, Hart-Smith in 1998 asked this question, and he also solved it because he showed that there is a space, H1 FIO, which is invariant under FIOs. And that statement alone is not particularly interesting because the zero subspace is also invariant under FIOs. But it also has the property that it's precisely in between this Sobolev space over the classical Hardy space and this other Sobolev space over the classical Hardy space. It's sandwiched in between them. And now when you combine these properties, you actually start to understand what Sigersog and Stein proved much better. Because what Sigersog and Stein proved is that an FIO maps this left-hand side all the way to this right-hand side. But what Hart-Smith realized is that that's not actually what happens. An FIO maps this space, H1 FIO, into itself. And it just so happens that this Sobolev space on the left is contained in H1 FIO, and H1 FIO happens to be contained in the space on the right. And then by interpolation, you recover the result by Sigersog and Stein, and by interpolating, you get back the estimates for LP as well. Now, somehow, I came across this work, and I think it's absolutely brilliant. Somehow, this really seemed to have not been noticed. The paper got cited quite a few times, but that's by the numerical analysis community, because he also introduced something called curvelets. But the harmonic analysis community, somehow this seems to have gone unnoticed, in part because it's quite technical. Because it's quite technical. Now, what we did, one of the first things which we did is we extended Hart's work. We did this for all P, and then you get similar properties. It's invariant under FIOs, and you have the associated Sobolev embeddings, which are just the same ones, but now different indices. Now, you should ask yourselves at this point 2 questions. One is, why do this? This has 3 answers. First of all, it's natural. I mean, invariant spaces have played a huge role in harmonic analysis and its applications to PDEs in the parabolic and elliptic theory. And often when things are natural, they're powerful. You could argue whether it's natural, but I'll try to show you in a bit that it is. And specifically, it relates to today's talk, because so far this talk is clearly very harmonic analytic. And I haven't mentioned a single semigroup. But actually this talk is extremely a semi-group talk, because so far, using the results by Seeger-Saugenstein and all the existing results up until the work by Smith and now these works by us, wave equations were not semi-groups on LP. They're not. They're so-called integrated semi-groups, but they're not semi-groups. But it turns out that in a way, the reason that they're not viewed as semi-groups is because in a way one looks at the wrong space when you consider them. You shouldn't consider them on LP, but they are a semi-group on these different spaces. And if you study them there, then you also understand what you still understand the results by Seeger-Saugenstein, but then you actually start to view wave solution operators, wave equations as semi-groups, as groups. It also leads to improved regularity for wave equations. Namely, the existing results tell you that FIOs, so solution operators to wave equations, if you want the solution to be in this space, for example, then you need it to be the initial data to be in this space. At least this function f and function g needs to be in this space with a -1 here. But these embeddings for these Hardy spaces for FIOs are sharp. And this space is bigger than this space, which means that you in fact can allow for more less regular initial data, and you still end up in this space. And in fact, because these embeddings are sharp, there are elements of this HPFIO which get really rough and which in fact are members of this space. And therefore there are elements which are way rougher than what you knew, so far you knew you needed, and you still end up with the solution in here. And all you need to be able to do is calculate whether they're in this space or not. And most importantly, it allows for iterative constructions, because now you can iterate on these spaces and this will appear in a bit, but before, whenever you applied an FIO and then applied another FIO and then another one, you would always jump and you would lose regularity in each step. Now you can iterate here, do that infinitely often, build a solution, and then apply the embeddings. Now I have a quick question for the host. How much time do I actually still have? Just to be sure, because of the break.
I think 10 minutes more. You can speak.
Okay, good. Thank you. Okay, so now we get to the question, what are these spaces? Now, one of the reasons why I think the brilliant work by Hart-Smith might have gone unnoticed is it's quite involved technically. At least when you first see it, it doesn't seem to be particularly natural. The original definition of this norm is actually more complicated than this, but this is a slightly simplified version, which involves an integral over 5 variables. You integrate over the cosphere bundle of Rn. So these omegas and these nus are angular directions. You have a low frequency part, which takes a function and only considers its lowest frequencies. These are sort of uninteresting. And then you have Fourier multipliers, which pick up frequencies of your function f in so-called dyadic parabolic regions. These are regions which you get when you take an annulus and you intersect it with a paraboloid. In Stein's book, this is called second dyadic decomposition. And then you integrate, you take a square function over some ball. And this ball, in fact, is more complicated than it seems, because it's not just the standard Euclidean metric. You have some sort of anisotropic metric from contact geometry. So it gets really complicated. We're not going to get into this. One of the things, the second question that I said there were 2 questions you should be asking yourselves. The second one is, what did we actually contribute? Because we didn't just put p's and 1 over p's in Hart's definition, in Smith's definition at arbitrary, relatively arbitrary points, and turned that into a paper. One of the things which we wanted to do is use tools from from modern harmonic analysis and also microlocal analysis to put all of this into a more effective framework. And one of the things you can do is you can consider the theory of tense spaces, which is a very powerful tool in harmonic analysis that is adapted to so-called doubling metric measure spaces. And this cosphere bundle is a doubling metric measure space. And then you can consider function spaces over this. That's the harmonic analytic part. Then you can use microlocal analysis and consider things which are called wave packet transforms, which take functions on Rn and lift them to to phase space, the cotangent bundle of Rn. So instead of having a function of one variable, you get functions of two variables. And then it turns out that these spaces, you can also view them in this way. Even though the expression for the norm, when you write it out, looks almost exactly the same, now you can use existing tools from tense space theory and microlocal analysis to really reduce the number of computations and to use existing theory to study these spaces. But that's still relatively complicated. The definition that I actually want to give you today is one that looks more natural and that might convince you that these spaces are in fact natural. Because you can also write them down in the following way. You again have some sort of low frequency parts. You take the lowest frequencies of f, because this function is compactly supported, and that part is uninteresting in practice. And then you do the following. Normal LP is just you take the LP norm of a function. Now, you don't take the LP norm of a function, but you fix a direction, omega. Then you take a paraboloid in the direction of that omega. And then you only look at the frequencies that your function f has in that direction. Then you get a new function, and you take the LP norm of that function. And then you do this for all directions, and you take the LP norm over the directions of this expression, which basically says that these HPFIO norms these spaces consist of keeping track of all the directions of your function in an explicit way. And the way in which you do that is you take paraboloids. And this recovers this idea in Seeger, Sogg, and Stein's work of using so-called dyadic parabolic pieces, which I didn't go into detail about. But it tells you that there's a different space which looks more complicated, but still somewhat natural. And this was for P between 1 and infinity. With Van Dieu and Song, we proved it for the case where P is 1, where I should note that they did by far the most work. The 2021 was because this one is going to get published this year. This isn't published this year, but yeah, we did it actually at almost the same time. This was slightly after my paper. Okay, so I think I still have time. Yes. So let me end with an application. Seeger, Sogg, and Stein proved their result for wave equations with smooth coefficients. Their result extends to these HPFIO spaces using the theory of FIOs for operators with smooth coefficients. But nothing has ever really been proved so far about the LP regularity, as far as I know, the optimal LP regularity for wave equations with rough coefficients. Using these spaces, what Andrew Hessel and I were able to do just a few months ago, actually, is to prove that you can obtain the optimal LP regularity for such equations. And what you need is C2 regularity of the coefficients. And then in dimension 2, you get a very nice statement. The statement is slightly more complicated in dimensions higher than 2, but in fact, I think we realized that we can also improve this. But inevitably in dimensions 4 and higher, it will be more complicated. The point is you can get, using then the Sobolev embeddings, if you know that it's well posed on HPFIO, then you also get the optimal LP regularity for such equations. And I should note to conclude that the 2 is not just some arbitrary number. This 2 is known to be sharp for various problems related to wave equations and hyperbolic equations in general. The 2 is very natural. You can understand this from a microlocal perspective, it's not, there's really an intuitive way to understand it. I don't know whether it's sharp here, but it's at least sharp in many problems. And the proof relies fundamentally on these HPFIO spaces because we build a solution using iterative constructions, using an infinite Neumann series. And unfortunately, you also have to use other things, paradifferential calculus, and you have to build approximate solutions using microlocal analysis. And here I have the details, but I guess it's better to stop here. Probably, right? Yeah, let me ask the... Right, I can just stop here to keep it. And these are some of the papers if you want to have a look at them. They're on the archive anyway.
Okay, thank you, Jan. Thank you for your interesting talk. And somebody has questions? Nobody? Okay, I have a question, Jan.
Sure.
With respect to your last slides, what about of this problem on bounded domains? For example, if you take omega in R2, satisfying some, for example, boundary conditions.
Well, yeah, okay. So
this last problem, if you consider in omega in R2, right?
Yeah. So I have to think about this. So one thing to note is that these AIs,
Yes.
these can be, these can of course be, you can of course go to domains, but of course boundary. Yeah, I would have to say I don't actually know. I mean, the theory of FIOs is adapted to manifolds, but boundaries is more complicated. Basically, I don't know. I think this is like, as far as I know, the first result along these lines. I have no idea.
But I suppose that the key point would be to define an object similar to an integral Fourier operator in this type of things, no? I suppose.
Well, yeah. Well, the thing is, that's a really good question. The point is that these FIOs are really nice, but you can only get them if you have smooth coefficients, because the way you actually show that the solution operators are smooth, are FIOs, are by using the smoothness. You solve infinitely many equations, and then you get this expression. So if you only have two derivatives, then it's hopeless. But so then and that's also what makes this difficult. Like you don't have any of the standard tools. You don't have nice expressions for the solution operators. So you have to really use more advanced techniques. And yeah, I don't know. It's a really good question, to be honest. I have no idea.
Okay, thank you, Jan. Valentin, you have a question? I'm going to...
Pardon, I have a question, but it's rather a comment. Yeah, that is it Jan? No?
Yes.
The speaker. Yeah, you said that they were on the wave equation. There were only integrated semigroups and not semigroups. Yeah.
Yeah.
But in the general theory of integrated semigroups, then it is known that when you have an integrated semigroup, then there are interpolation and also extrapolation spaces on which you have semigroups.
Yeah.
I think so. The interest in the paper or in the talk, in the presentation, the result here, very interesting, is that probably this space HP sub FIO might be one of those interpolation spaces given by the general theory.
Yes, indeed. So I was slightly, because of time reasons, slightly imprecise, or in fact, that was not true. Abstractly, you can show, but this is in fact what I mentioned also, what Hart also realized, there has to be an invariant space.
Yeah.
So this is what I meant at the time. For
Yeah.
reasons, you can see that there has to be an invariant space.
Yeah, so just simply saying that, so it is known, but this has not been, in a way, to my knowledge, has not been done in a concrete way as you have done in your work. Yeah?
Well, it's also the fact, I don't know, in terms of the semi-group bit, then you get a space, as far as I understand, but maybe you can correct me, which is invariant under one semi-group. The magical thing about these Hardy spaces for FIOs is that they're simultaneously, you get semi-groups associated with all smooth wave equations. So it's not just a simple...
So you're right, is that in the general theory, you start with an integrated semigroup and you find the space on which, so you get the part of that operator generates a semigroup.
Yes, yeah, but as far as I know, this is adapted to the semigroup, right?
Yeah. Now, on the other hand, let me just say one thing about the case of a bounded domain. The case of a bounded domain with the general elliptic operators of, let's say, with L infinity coefficients. There are some results there, but in terms of, again, in terms of integrated semigroups, but no results concerning the optimal results, optimal regularity as you have in the presentation here.
For the elliptic case.
That's it. For example, in the book by Elmati Ouabaz, he has some sections about the wave and the Schrödinger.
Yeah, I know. Yeah, I know. But it's really like you said, the problem is this -1. So if I'm not mistaken, using the theory of spectral multipliers, which is also really involved, you can get the n/2.
They do get that. Yeah. So, and actually, with from semigroups, I think there was a paper by Pedro and his collaborators where they were able to get to this constant, but for the classical wave equation, the constant coefficients, they had this constant from semigroup theory. And there are other places where there can also be achieved from the Laplace transform, using Laplace transforms.
Okay.
Thank you very much for this nice presentation.
Yeah, thank you for your question. Those are good questions, good comments and questions.
Okay. Somebody has any more questions? Okay, thank you so much.
I want to ask one short question to Jan. What about the asymptotic behavior or the solution? You can say something about this, and in this way we join with the talk of Sachi that is going to be about stability.
Well, yeah, it's a really good question. So in the case of probably the answer is that it's where is it? That it involves the same index. This would be my guess. So there's a similar. For Schrödinger type equations, you can do something similar as all of this, which involves different spaces called modulation spaces. And there you see, there much more is known, and you see the same type of phenomenon where on these invariant spaces, yes, so there's a phenomenon, and there you see you have a different index, but then it grows as t to the power that index. And also when you look at the result for the classical wave equation, so where is it? This one, you know that it grows as t to the power this index, if I'm not mistaken, which doesn't mean that it has to grow like that on HPFIO, but I would guess that it's t to this power. Yeah, but I don't know. I mean, I have no idea, but that would be my guess.
Okay, thank you.
Yeah, thank you for the question.
Okay, thank you so much, Jan. Now I'm going to continue with the last talk in the meeting. Also, this talk is included in our week seminary, Rubio de Francia. And next speaker is Sachi Srivastava. Sachi?
Hi, I'm here. Shall I just?
If you want, you can put your, okay, good camera.
Yeah.
And Sachi is going to speak about the light semigroups and stability. Thank you for accept your to speak here. Okay.
Can I share my screen now?
Sorry.
I'll just share my screen.
Yes. Now is yes. Now I'm able to see. Okay.
Yep.
Yep. Perfect.
Just give me a minute. Okay. So thank you very much for inviting me to speak here. It's a pleasure to be here. And I'm going to speak on, so the title of my talk is Stability and Delay Semigroups on Banach Spaces. But I have to confess, this is really going to be polynomial stability and on Hilbert spaces mostly. So since this is a semi-group day, I guess I should straight away begin with the abstract Cauchy problem. Before I start, let me, taking my cue from Jan, say that this work, the ongoing part of this work is supported by a CRG grant from the Department of Science and Technology, the Government of India. And some of this work has been done jointly with my PhD student, Sharad Rastogi. So here we go. So I have to start with the abstract Cauchy problem, which we all know. So for a Banach space X and a closed linear operator on X, U dash T is AUT and U0 is X naught is the usual abstract Cauchy problem. And we have usually two types of solutions we talk about, the classical solution and the mild solution for this. And the semigroups are not far behind. So for a closed linear operator, the following assertions are equivalent. A generates a C0 semigroup. For every X, there's a mild solution of the abstract Cauchy problem. Or for all X in the domain of A, there is a unique classical solution of ACP. And when, of course, we know when these assertions hold, the solution is given in this way. So where I'm heading to is to just tell you what I mean by what my setup for the delay semigroup is going to be. What does one mean by a delay semigroup? Usually we use all this powerful machinery to address PDEs, to find solutions or study solutions of PDEs. But if we have PDEs with some delay terms, then it is useful to look at the associated delay semigroup. So for example, very simple equations here, and you can see the term here with the delay. Okay, hopefully we can study more complicated things, but just to give a flavor what I mean here. So to that end, we have what we are called an abstract delay differential equation, which is U dash T is BUT plus phi UT, and U0 is X, and you have U0 is some F. Everything is appropriately chosen. And for the purpose of this talk, our standing assumptions will be that B is the generator of a C0 semigroup. F takes values in LP minus 1, 0, X. Phi is the important thing called the delay operator. And I am only going to be dealing with bounded operators from W1P to X. And UT, as is usual, is given in this way. So this is what we call the abstract delay differential equation. And I'd like to mention here that most of this that I'm talking about has been developed, is following the format of in the book by Andras Batkai and Susanna Pereira from Rainer Nagel's group. So I have not given any references for the standard stuff, but that is where this is from. And then once we have an ADDE, sorry, this should be ADDE, an abstract delay differential equation, not DE, we can associate, and I fix my P here, of course, and we can associate this matrix operator with this. It is a 2x2 operator matrix with entries B, phi, and D by D sigma. The domain is always taken to be in this way. And once we do that, I can write the abstract delay differential equation as an abstract Cauchy problem on the correct phase space. And then the solutions of ACP and of ADDE are in a one-to-one correspondence in the following manner. So all this is pretty well known, standard stuff. And the semigroup, if ADA generates a C0 semigroup, then we call it a delay semigroup. Okay. So this is what we are working with. And I'm going to look at, try and relate the stability of polynomial stability really of the delay semigroup with all the ingredients given to us. Let me say a word about the delay operator. We always assume the delay operator to satisfy a technical condition, which is called admissibility. I will not mention what it is here, but most of it's pretty, in the class of admissible delay operators will contain a pretty big class of delay operators that appear. And when I take a particular eta here, then we get a simple discrete delay operator, which is, both of these are of course admissible. So much for delay operator, delay semigroup and the delay operators that are assumed. Gosh, something is going wrong with my screen here. Sorry. So what kind of stability? As I already mentioned, I'm going to talk about polynomial stability here. But in general, one would talk about, for a given C0 semigroup, the first type of stability, the decay we talk is if the rate is exponential and the decay is in norm. That is called the uniformly exponential stable semigroup. When we restrict to just the decay of classical solutions, we call it exponentially stable. And the next type, which is widely studied, is strongly stable. When we just have individual orbits going to zero, there's no uniform rate. For delay semigroups, there is really a lot of literature on uniform exponential stability. And to some extent, even strongly stable semigroups have been studied. So polynomial stability falls somewhere between the second and third type of stability. And let me go to that. What I mean by polynomial stability for a C0 semigroup. There might be slightly, there are different versions of polynomial stability that exist in the literature. but I think by now this is widely accepted if you allow uniform boundedness. So a C0 semigroup on a Banach space is with a generator B is polynomially stable with power alpha greater than 0 if the semigroup is uniformly bounded. The imaginary axis is completely in the resolvent set, and the following estimate is satisfied. So the classical solutions decay at this rate. And several people have studied polynomial stability over the last decade. So I mentioned Batkai, Angel, and Proust, and Schonberg, Batty and Ducatis, Borikev and Tomilov, Panonen, and Rozendaal and Verar. So I might mention Rozendaal and Verar they do not work so much with uniformly bounded semigroups, but mostly, and maybe the first authors here do not necessarily work with uniform boundedness, but uniform boundedness is now pretty much taken as part of the polynomial stable semigroups. So as I said, this definition, we are going to be working with Hilbert spaces because life has been made easier for us by some results by Borikev and Tomilov, which allow us to characterize this condition under uniform boundedness uh, assumptions into some resolvent decay conditions or resolvent estimates, shall we say. So here is what I mean by that. So if we are working on a Hilbert space, then for a polynomial, to show that a semigroup is polynomially stable, if of course there is uniform boundedness and the imaginary axis is on the resolvent set, and the norms of the resolvent on the imaginary axis are big O, behave like big O of mod S to the power alpha. And recalling that this is what I mean by mod big O of mod S alpha, that there is a function from a real valued function on R behaves like is a big O of mod S alpha if this condition is satisfied. Mod Fs is less than equal to m times mod S to the power alpha for all S after a certain interval around 0. One more point that can be I should mention it, and people might be wondering, here is a real number, there is a mistake here. This alpha has to be strictly greater than 0, of course. But we keep saying polynomial stability, it's widely accepted, but there is not just polynomials here. We are talking about t to the power 1 over alpha in the first definition. I'll just show you here. Okay, so it's not necessarily integral powers. So this is for general polynomial stability definitions on Hilbert spaces, and I might mention this characterization is due to Borikov and Tomilov. So now we step it to delay semigroups. So when is the question would be, when is a delay semigroup, the way I have just defined it, polynomially stable? So the first results that we have in this context is this. So if the underlying semigroup is polynomially stable, I beg your pardon, this alpha has to be always strictly positive. Somehow it's become less greater than equal to. Please ignore the equal sign there. So B is the generator of a polynomially stable semigroup, and phi is admissible. And if this supremum of phi lambdas, norm phi lambda r lambda b, is bounded by a number strictly less than 1, then we at least have that the spectrum of the generator of the delay semigroup lies to the left. No, right now I cannot say it lies to the left. It does not intersect the imaginary axis, and the norm of the resolvent on the imaginary axis is big O of mod S alpha. If in addition, the delay semigroup generated by A is also uniformly bounded, then the semigroup is also, the delay semigroup is also polynomially stable with the same power on the Hilbert space H cross L2 minus 1, 0, H. Just to let you know what I mean by phi lambda. Phi lambda is just this bounded operator involving the exponential function here. So this theorem already brings out the problem that we face. Uniform boundedness is the difficult bit to prove. So that is why that has to be assumed additionally. For the first part, it is the proof. The idea of proof is pretty straightforward. It depends on two well-known, we use these two well-known ideas from the theory of delay semigroups, that the spectrum of the generator of the delay semigroup and the spectrum of this operator B plus phi lambda. Okay, so you can see I made the slides in haste. This is capital phi. They are related in this way. And the resolvent of A at lambda is expressible as a 2 cross 2 matrix in terms of these expressions. And then we estimate the norm. So this part we are able to achieve. For the uniform boundedness, we do not have a general format for every admissible phi. But it turns out that for some phi's, which I have mentioned already, we already are able to prove uniform boundedness, and we can get polynomial stability. So if we have phi as a discrete delay operator, which I mentioned earlier also, which is of the form summation ck's acting on f of minus hk. The ck's are bounded operators on h, and hk's are fixed scalars between 0 and 1. Then if we have this condition, which is the corresponding condition from the previous theorem, and it looks like this in this particular case of phi, then the delay semigroup is polynomially stable. Okay. We can also get a similar conclusion for phi's of this form. You'll see that in general, for a general admissible phi, this is difficult to prove in this following way. Okay, let's go on. Then we have attempted to again come to study polynomial stability by a slightly so a quick example, which is really I would consider a baby example, because it's not really coming from a very nice PD. But if I take B to be a multiplication operator, suitable multiplication operator on L2, then it has been shown by why are my slides not showing completely? Can anybody help me with this? Sorry. Okay. So this has been shown by Panonen to generate a polynomially stable C0 semigroup. And if I take a very simple delay operator of this type, I just take K to be 1. I take a single bounded operator in H, and I define my C in this form, then it is not difficult to show that this delay semigroup generator will be polynomially stable. Okay, so much for this line of reasoning. And by another approach to polynomial stability of delay semigroups, we can show this involves some fractional powers. So if B is the generator for polynomially stable C0 semigroup on a Hilbert space, and of course phi is admissible, and this strange looking range condition is satisfied, then there exists a delta greater than 0 such that if this operator here, the norm satisfies, is less than delta for all real lambda greater than equal to 0, then the spectrum of the generator of the delay semigroup is contained in the negative complex plane, the left-hand part of the complex plane, and we have a required resolvent estimate already. If in addition A generates a uniformly bounded semigroup, then the delay semigroup is also polynomially stable. So again, here there is a problem with uniform boundedness. It doesn't fall into our lap just because dB is a generator of a polynomially stable C0 semigroup. And another simple example to show that such things can exist, I pick up another example from Pannonen, where a TT is just the multiplication semigroup of this type. And the domain omega is chosen in a rather strange way to ensure polynomial stability. And you can see this is sort of asymptotic near the imaginary axis in a way. And then a simple phi, a discrete phi, will do the trick. This is again a simple phi discrete with a single operator C. And we can show that the conditions of the previous theorem are satisfied, and we can get a polynomially stable delay semigroup. Okay. So finally, to the last part of my talk, I should first say that stability, the strong stability and polynomial stability and perturbations, there are very few results about strong stability and perturbation. So in keeping that in mind, let me tell you this result, that if we have this, that if B is the generator for polynomially stable C0 semigroup, and C is a closed linear operator satisfying its domain is doing the right thing with respect to B, and if we have some norm, some bound for this quantities here, norm of C R lambda B, and appropriately for C on the right hand, R lambda B C, then B plus C generates a polynomially stable semigroup with the same power. So the fact that B plus C generates a C0 semigroup is due to Batty. We do not contribute anything here. The fact that it turns out to be polynomially stable is our contribution. So we are able to show, and actually the proof really depends on being able to show again that the resolvent of B plus C is somehow is dominated by a constant times resolvent of R lambda B. And that allows us also, in this case, to be able to deduce uniform boundedness of the semigroup, of the delay semigroup. We have a similar corresponding result for just strong stability. This is for polynomial stable, which is just saying that if BDB is strongly stable and uniformly bounded, then, and C is an appropriate operator satisfying these conditions A and B, same conditions as the previous theorem, then the perturbed semigroup is uniformly bounded and strongly stable. And how do we use this? Of course, people who are familiar with delay semigroups know that a delay semigroup can be thought of as a perturbed semigroup in the following sense. You can write the generator A, which is actually B. A is a 2 cross 2 operator matrix with entries B, phi, 0, and D by D sigma. And here we can write it in this form. A naught plus C, where A naught is this operator. It has the same domain as the generator of the delay semigroup. And C is the operator here. And now I can apply my previous result on general result on perturbation of a polynomially stable semigroup to A naught and C, provided I know that A naught generates a polynomially stable semigroup. That turns out to be not difficult to do. It's straightforward to check that if BDB is the generator of a C0 semigroup TT on a Hilbert space, then TT is polynomially stable if and only if this operator semigroup generated by curly A0 is polynomially stable. Once we have that, we can apply our perturbation result to get this particular result for polynomial stability of the delay semigroup. These are a little horrible looking conditions, but again, for simple phi, they can become quite manageable for particular phis. Okay, I think I'll stop here. Here are my references. This paper is to appear in Journal of Evolution Equations. And where is the book? Okay, so this book seems to be missing, but this is I would, anybody interested in delay semigroups, I would recommend this book by Batka and Piazzera, which I have referred to very heavily, often without mentioning. Thank you. So I'll stop here.
Thank you, Sachi.
Thank you.
Thank you for the talk. I'm going to ask if somebody has some questions. Perfecto, adelante. Okay, Jan.
Hi, Sachi. Yeah, I really liked your talk. I actually have two questions.
Right.
One is you consider polynomial behavior, polynomial decay, and you mentioned the result by Borichev and Tomilov. But yeah, as you maybe know, this was later extended by Badichil and Tomilov to more general decay rates.
Yes.
And by now it's known you have the same type of characterization for much more general decay rates. With Seifert and Stan, we did this in a much more general setting. Is there any way you could do the type of things you do for more general decay rates?
Yes, you're talking of that function M log.
Not M log, the M, so Badi and Ducard did it for M log, but Badichil and Tomilov did it for M, and then Seifert, Stan, and me did it also for M in more generality. Yeah,
let's say that it's part of the ongoing work. It gets quite messy, but doable. I mean, I think what would be, of course, we are looking at it, but we are trying to look at more concrete equations first and see what where it would lead us, and then if it's worth doing.
Yeah, we had it for viscoelastic damping. That's where you encountered non-abstract cases or relatively non-abstract cases where you actually have non-polynomial decay behavior.
Yeah.
Anyway.
Yeah. I mean, yeah, thank you. Yes, it's part of the project, but we'll get to it.
Okay, yeah. I also have a second question, but maybe someone else wants to go first. I don't know.
Okay. Thank you, Jan. Any more questions? Okay. If nobody has more questions, we say thanks all the time to Sachi. And
have another question?
Yeah.
okay. Do you have another question?
Yeah,
okay,
yeah.
You can continue, Jan. You can continue.
We can take it.
So you mentioned the fact that to some extent the most difficult part is proving uniform boundedness. And
yes.
Precisely one of the reasons why Mark Ferrar and I started doing that stuff is because we also knew that, for example, Lassi Pannonen and David Seifert also ran into that problem. And there are still things that you can say about the actual decay rate, even when you don't have uniform boundedness. Does that allow you to consider more general equations if you only are interested in the decay rate and not in the uniform boundedness?
So the problem for us was that, I mean, everything is depending on being able, because we are able to translate it from going from the semi-group to the resolvent estimates. Yeah. And for the delay semi-group, you have a very nice expression for the you have a 2x, not nice, but at least you have an expression 2x2 matrix. So we did try to attempt to do what your paper has, where you don't need uniform boundedness, but significant difficulties because you have power, but maybe we can think about it and do something there.
No, yeah, it's because you said that the uniform boundedness seems to be the most difficult part, but yeah. Okay, and thank you.
Okay. Any more questions or comments? Okay, thank you. Another time now, yes, Sachi. Okay, we have finished the meeting. I would like to thank two speakers, also the whole audience by assist to this meeting. I have enjoyed a lot, and I hope that we meet another time in the next month in another congress, maybe. And if nobody has anything to do to say, we are going to finish. Okay, thank you so much.
Thank you.
Thank you very much. Thank you, Pedro, and thank you, Luciano. Are people going to the Europe ECM? Do we meet there? Now it's online.
I'm going to the ECM, but probably just online, yes.
Okay. Yes, that's what we mean. Okay, see you there then. Okay, bye-bye. Thank you again.
Bye.
Thank you. Thank you. Oh, by the way, I had a comment. Maybe the semi-groups, the two semi-groups that Luciano mentioned, they're definitely stable, I think. Contractive.
Sorry?
Your semi-groups, are they polynomially stable?
I think no. I think that there were contraction semigroups, but I suppose that there exists.
Spectrum is on the right part of the complex plane.
No, the imaginary part is contained in the spectrum.
Yes, but you don't know whether the spectrum is completely on the left. I thought there was one.
The spectrum is on the left, including the imaginary edges.
Mm-hmm. Okay, yeah. Then we have no chance. Thank you.
Yes.
Will
Okay.
you Will you upload videos to your page?
For me, sorry.
Will you upload videos on the page, on your page?
Pedro,
Yes.
maybe
Yeah.
we put the videos on the web page. Could be.
Yeah. Okay. I stop.